Hello everyone. In this class I am going to discuss about 2-bit up-down ripple counter and modulo counter. I am going to introduce you modulo counter, and in the last class we have discussed up counter separately and down counter separately for the asynchronous counter, and we know that asynchronous counter is otherwise said to be ripple counter. Okay. So here also I am going to discuss about the 2-bit up-down counter. So here for going with the up sequence and the down sequence, because you need to intimate your counter that count up or count down. For that we need one more control bit. Let the control bit be M. Okay, let the control bit be M. So if M is equal to 0, let it be up counter, and M is equal to 1, let it be down counter. Okay. So now for M is equal to 0, it is up counter, M is equal to 1 down counter. Why am I taking 8 status? See Q and Q bar, let it be the states. See for Q, if I am taking for the successive bits, for the successive flip-flop bits, if I am taking the clock from the Q, that will be your up counter. And if I am taking the clock from Q bar, that will be your down counter, that we have already discussed in the last class, right? So I am taking Q and Q bar of the previous states, okay, of the previous states. So this will be again 0 0. So 3-bit combinations all 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1. So altogether you will be having 8 states, okay. From 0 to 7 it is 8 states. That is your present state. So coming to your next state, okay, coming to your next state. So again it is Q plus and Q bar plus, let it be. So if my 0 0, if my input or my current state is 0 0, and if my mode bit is 0, it means an up counter. So if current state is 0 0, it will be 0 1, and 0 1 means 1 0 1 1, and then it will go ahead with 0 0 again. And now your bit changes to mode bit change from 1, so it will be a down counter. If it is if the current state is 0 0, it will go ahead with 1 1, and then it will be 0 if the current state is 0 1, okay, it will be 1 0. So if my current state is 0 1, I am sorry, I have written wrongly. If my current state is present state is 0 1, okay, my down counter, it has to be 0 0, and if it is 1 0, and it has to be 0 1, and if it is 1 1, it has to be 1 0, okay, right. So this is going to be how am I going to give the clock? That will be your input. That is what you need to design, meaning the clock 1 for your second flip flop, because it's a 2-bit counter, right? So for the second flip flop, so this clock for the first 4, it will be same as Q, okay, and for the next 4, it will be Q bar, okay. Let me fill this up. So first 4, it will be Q means 0 0 1 1, and the next 4, it is your Q bar means 0 1 0 1. We need to design the combination logic circuit for this clock. So let me take a K map. So K map with the mode bit and your present state, that will be your inputs, right? So Q bar. So we will be having 8 states. Mode can be 0 1 1. This is 0 0 0 1 1 1 and 1 0. And now if I fill this up, so first is 0 0 and 1 1, and then 0 again, 1, 1 and 0. Okay. So if I take this down, I'll be making a combination like this, right? So that is nothing but m bar into whichever is common q plus this one is m into q bar. Either I can use one AND gate. This is my clock one. Okay. So I can use 1, 2 AND gates, one for m q bar, another for m bar q, and then take an OR gate and then give it to your clock one. Okay, give it to your clock one. This can be a combination circuit, or see, look here, this is nothing but an XOR, right? So it is M XOR Q. Okay, in either way you can decide. So coming to your up down counter, the timing diagram. Before the timing diagram, I need to design this. So here what am I going to do? Let me draw the circuit first. Okay. So we need 2 flip-flops, J and K flip-flop. I am going to take JK. I mean, let it be J1, K1, J0, K0. So this will be a Q0, Q0 bar, Q1, Q1 bar, and then the clock. First, let me give the input. This is tied high. This is also tied high. So the clock, let it be a negative edge triggered clock. And here my clock 1 will be I have one more mode bit. Okay. Mode bit can be 0 and 1. And it may be, if it is, okay, that should be an active low because I am using an inverter, right? Okay. So from here, this mode control bit, I'll be, if I'm using an inverter like this, I'll be taking, this is M, if I'm taking M, this will be M bar and this will be Q0. And this will be Q0 bar. And then I'll have an OR gate. This will be my clock 1. So clock 1 will be tied here. So this Q0 is from here. In Q0 bar, I will be taking it here. I can draw like this. Otherwise, I can use a simple XOR. I'll take from Q0 and M directly, and this will be clock 1. Okay. So Q0 is from this point and M from this point. Okay. This is the circuit diagram. So coming to your timing diagram. So I'll be having clocks first. So mode is initially high. Let me take like this. So whenever your mode is high, it will be an up counter. Let's check. Whenever your mode is low, it is your up counter, right? This is an actually, for this case, it's an active low. Okay, means high means it's an active low here. Okay, keep that in mind. So we have 0 and 1. So let me assume this Q1 and first Q0 and Q0 bar. Okay, because this is going to be the clock for the positive half cycle, and this is, assume that first initially it is 0. Okay, whenever your mode is 0, so whenever your mode is 0, I have taken this as an down counter initially. Let me take an up counter. Okay. So whenever your mode is 0, this will be acting as an up counter. So up counter, we now assume that initially your 0 first, and then go ahead with 1, 0. For each clock transition, your Q0 will be like this, continuously. Okay, and Q0 bar is a vice versa, like it's a complement, just the complement of Q0 is your Q0 bar. Keep in mind your Q0 going to be your LSB of your counter, Q1 is going to be your MSB of your counter. So this is about your Q0. What about your Q1? First let it be this clock. This is clock initially because it's an up counter. So Q1, so for that case, this is going to be your clock. Till then it is 0, assume initially 0, and afterwards it's 0, so it is going to be 1 here, and this is going to be 1 here, like this. Okay, so let me go ahead with this. This is going to be 0 1, initially it is 0 0, 0 1, 1 0, 1 1. So the up counter operation is stopped here, meaning the counting operation is over. Okay, so counting operation is over from this point of time. So what about your next case, meaning your down counter case? Okay, let us go ahead with that. Okay, let me assume for the next consecutive bits my mode bit is high. Okay, so when my mode bit is high, so it will be acting as an, this is my up counter, this is my down counter. Okay, so now QA is not going to change anyway, only your Q1 is not going to change anyway because same clock is being applied here. I am giving my mode bit 1 here, okay, 1 here, so here only. So if you look at it here, the clock edge is here, so it will be 0 now, but here your mode is going to be high, so it will be retained 0, this Q1, till my next clock edge. Now my clock is Q0 bar, so here, so toggle to high from low. Okay, so now this is going to be my clock pulse. So look here, this is 0 and 0, 1 1, 1, 0, 0, 1, 0, 0. So this is going to be my, after my mode bit is 1, and this is going to be my down count. Okay. So this is how your up down counter will function. Next we will go ahead with the modulo counter. So what is that modulo N counter? For example, if a counter, if I need to start and count from 0, 0, from 0, 1, I am writing in decimal, okay, 2, 3, 4, 5, I need up to 5, mod 5, okay, N is the number of states that is required, okay, so I need only this many number of states, okay. So now it is like I have 2, 4, 6 states. So however, how many flip flops I will be having? I will be using it. I will be using this 2 power 3, which is nothing but 8 states. From 0, 0, 0, it has to end up with 1, 1, 1. That is how we have designed the counter till now. But we know don't want the count after 5. So 6, 7, 8 should be ruled, okay, should be ruled. I need to design a counter such that it has to start from all 0 to 101. How to stop this? So we need 3 flip flops for 3 bits. So let me take 3 flip flops here. So I will be having a clock for all the flip flops. Either I can use a T or JK flip flop for the ripple counter. Let it be a T flip flop now. So for each and every flip flop I have a reset button also. Okay. Reset is nothing but it will go back to the initial state. It will go back to the initial state. From 5, when it counts up from 0, 1, 2, 3, 4, 5, it has to go back to the initial state. So how to do this? So let me take NAND gate. So for the 5, bit number 5, so this is my Q0, this is LSB, this is my MSB, this is my Q1, and this is going to be my Q2. So let it be Q0, Q1 and Q2, let me take it out. This is going to be 101, that will be the final state, am I right? For example, I am telling. So this Q0, Q1 and Q2, I am going to give this is my output 101, of which I am going to select 2 bits. This is my Q0, this is my Q2, this is my Q1. So let me take Q0 and Q2, okay. I will be taking this 1 and 1, okay. Let this one goes here to all the reset. And reset, let me assume that when reset is high, all the flip flop will be resetted to the initial state 0, 0, 0. So automatically, so from 0, 1, 2, 3, 4, 5. So for each and every case, so from 0, Q0, Q1, Q2 will be fed. I mean Q0 and Q2 will be fed. Sorry, Q1 won't be fed to this AND gate. Q0 and Q2 will be fed. So whenever this 2 bits is 1 and 1, automatically it will be resetted. Again it will go resetted in the sense, make it all 0. Come back to the original state and start counting up again. Okay. So from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1 and 1, 0, 0, 1, 0, 1. See, only for 5 you will be having this 2 bits 1. So Q0 and Q2 has to be fed to your AND gate. This is your modulo 5 counter. Okay, this is your modulo 5 counter. The same way, the decimal value also can be, decimal counter can also be done. So the decimal counter, as we know, from 0 to 9 we need to count, am I right? From 0 to 9 we need to count, and after this we need 4 bits for this, because 1001 is your 9, so we need 4 flip-flops. Okay, again what you need to do, this will be your this is Q0, 1, 2, 3. So Q0 and Q3 has to be given to your AND gate, and this has to be fed to all the reset. Okay. If reset is high, meaning if one is given, in fact it depends on the IC number. If one has to be given for the reset, means all the flip-flop will be resetted. If 0 has to be fed for resetting the particular flip-flop, then you can use an AND gate. That depends on the IC. Okay. So for this 0 to 9, it's a decimal counter, otherwise said to be a decade counter. Modulo counter, modulo decimal counter, BCD counter, or a decade counter. It's a modulo counter also, modulo N counter also. Modulo N means N is 9 here. Okay. With this I will stop today. Thank you.